Hi everybody, today we are going to try another flipped classroom lesson, and today we're going to talk about the equilibrium constant, and we're going to try a new program called Explain Everything on the iPad. But before we do that, gotta say hi to Simmergy because he asked me to send a shout out to him, so there's my shout out. Also today my kids aren't in this one, I'm sorry, next time. Alright, so before we talk about the equilibrium constant, we have to learn more about it. And the way I'm going to teach you about it today is by deriving it for you. So hopefully you remember how to write a rate law or how to get the rate law for something. So we're going to do it for this reaction here. And this reaction is reversible. So it will have a forward reaction and a reverse reaction. So we're going to do the rate law for both. So the rate of the forward reaction equals the Kf of the forward reaction times the concentration of the reactant. Now, in this particular case, we're going to consider this an elementary reaction, so the stoichiometry, this invisible one here, will be right here. And because it's a 1, you don't have to put it in. So that's the rate law for the forward reaction. Now here's the reverse reaction, and you can also have a reaction for the or a rate law for the reverse reaction. So the rate of the reverse reaction again equals the K of the reverse reaction times what we consider the reactants in this reaction. Now because there's a 2 there, we also have to put a 2 in the rate law expression. So there is the rate law for the reverse reaction. So at equilibrium, you should know that the rate of the forward reaction equals the rate of the reverse reaction. And because of that, we can set those two rate laws that we just derived, we can actually set them equal to one another since the rates are equal. So Kf and 204 is equal to Kr NO2 and squared. Now if we solve for Kf over Kr, then we'll have this equation here, and what you'll notice is the products are on top. And the reason we're doing this is because Kf over Kr actually equals Kc. And that's what the equilibrium constant is, Kc. Kc in some textbooks is also written as Keq. So we've now derived the equilibrium constant. Now, one thing you should notice about this is that the equilibrium constant, Kc, is the concentration of the products over the concentration of the reactants. And all of this is always at equilibrium. So when you put these concentrations in, they have to be at equilibrium. So right now we have a generic equation right here. And this generic equation, we are now going to write the equilibrium expression for it. And on the last page, we talked about how products go on top and reactants go on the bottom. Now again, we're going to assume this is an elementary reaction and that those A's and B's, or the stoichiometric coefficient, those are going to be our exponents. So products on top, so that's C to the exponent C, D to the exponent D, all over A to the exponent A, and B to the exponent B. Now that's a generic equilibrium expression for a generic chemical reaction. Now again, not trying to repeat myself, but only concentrations at equilibrium can go into the equilibrium expression. So if you have initial values, they can't go into the equilibrium expression, only equilibrium concentrations. Really, really important. So where do those values come from? Where do those concentrations come from? Well, they come from doing the experiment and then finding out what the concentration is at equilibrium by a variety of methods. We're going to talk about those methods a little later. But here you have some data. You have 4 experiments, and each of those experiments started with a particular amount of product and a particular amount of reactant. So here are those initial concentrations. And those initial concentrations, they're put together, and then once the system's at equilibrium, the equilibrium concentrations are then found. Now these values, these equilibrium concentration values, are then substituted into the equilibrium expression, and a Kc value occurs or is calculated. That Kc value, you'll notice, it doesn't matter what we start with, what our initial values are. The Kc value is always the same. And that's because Kc is actually a ratio of products over reactants. And that ratio is what equilibrium is, and it stays the same. You can approach equilibrium from either direction. You can start with products, or you can start with reactants. It doesn't matter. You always get the same Kc value. So what does K mean? Well, K tells you if the forward reaction is favored or if the reverse reaction is favored. So if K is larger than 1, that means that most of the reactants are converted into products. And if K is smaller than 1, then that means that most of the reactants stay as reactants, or the reverse reaction is favored. And when we say K is less than 1, that generally means that you've got K values that are equal to like 1.3 times 10 to the negative 3. That's what we mean by less than 1. So if K is greater than 1, you have lots of reactants turning into products, and that's considered a reaction where the forward reaction is favored. And if you have a K that's less than 1 but greater than 0, then you have most of the reactants staying as reactants or products being turned into reactants, and that's called a reaction where the reverse reaction is favored. Finally, we're just going to talk a little bit about how you can manipulate equilibrium constants. Now, here is, again, the forward reaction, and here I have the Kc, or the equilibrium expression, already derived for you. And I also have told you what the Kc value is. It's 0.212. Now, I could ask you in a question, what is the Kc value for the reverse reaction? Because by now you should know that there's a Kc for the forward reaction and a Kc for the reverse reaction. So if we reverse the reaction, again, your equilibrium expression is different. But if you want to know that Kc value, you just take the reciprocal of the forward reaction. So that Kc value here is right there. And when you take the reciprocal of it, you get a new number, and that's now the Kc for the reverse reaction. So that's the lesson for today. Tomorrow we're going to talk about ICE tables, and it's a way of calculating different amounts in a reaction that's at equilibrium, or that a reaction that is going to equilibrium. So we've already talked about the I, and we've already talked about the E in ICE tables. The I is the initial concentrations, and the E is equilibrium concentrations. So tomorrow morning I'm going to ask you, what do you think that C stands for? All right, well, see you tomorrow. Have a good night, guys.